China didn't just build the world's largest oil refinery. They built the island it sits on first. You're looking at the Zhejiang Petrochemical Complex, a facility so massive it processes over 800,000 barrels of crude oil every single day. That's enough refined fuel to fill more than 1,200 Olympic swimming pools every 24 hours. You heard that right, 1,200 pools, daily, from a single complex sitting on land that didn't exist 30 years ago. This isn't a refinery that was built near the coast. It was built on the sea itself, on reclaimed land, engineered from the ocean floor up, in one of the most ambitious industrial projects any country has ever attempted. And the engineering behind it? Most people have no idea how deep this rabbit hole goes. The island that wasn't there. Picture the Zhoushan archipelago off the eastern coast of China, a scattered chain of islands surrounded by deep open water. No flat land, no industrial zone, no foundation for anything, just sea, tidal current, and rock. And yet, Chinese engineers looked at this location and didn't see an obstacle. They saw the perfect site for the largest oil refinery on the planet. Why here? Because Zhoushan sits at the intersection of some of the world's busiest maritime shipping lanes. The water is deep enough to receive the largest crude oil tankers ever built. The location puts the refinery within reach of both domestic Chinese markets and international supply routes. Building here wasn't just logical, it was strategic. But logic and strategy don't move mountains. And in this case, they had to move the sea floor. The decision to reclaim land rather than find an existing site wasn't made lightly. The alternative building inland, or on existing coastal land, would have meant sacrificing the deep water port access that makes this entire operation viable. Without the port, there's no refinery. Without the location, there's no port. Everything pointed back to one answer: build the land yourself. But this was just the beginning of a challenge that had never been attempted at this scale before. The reclamation footprint required for the Zhejiang complex covered thousands of acres of open water. Engineers weren't just filling in a shallow bay, they were constructing an entirely new landmass in a tidal zone, subject to constant wave pressure, storm surges, and shifting currents. The margin for error was essentially zero, because the infrastructure that would eventually sit on top of this land would weigh millions of tons. And here's what makes that so staggering. The island had to be ready before a single piece of refinery equipment could arrive. You couldn't test it under load gradually. You had to get it right the first time. On ground, you built yourself, in the middle of the ocean. China didn't just choose a location, they manufactured one. And what came next, the process of actually pulling solid ground out of open water, pushed the limits of what modern engineering thought was possible. Moving the seafloor. You don't build on water, you replace it. That's the fundamental principle behind land reclamation, and at Zhoushan, it played out at a scale that's almost impossible to visualize. The process started with dredging enormous hydraulic dredgers pulling sand, sediment, and material from the sea floor and pumping it into the designated reclamation zone. These weren't small operations. The dredgers working on projects of this scale can move tens of thousands of cubic yards of material per day. And the Zhejiang complex required this process to continue without interruption across a footprint measured in thousands of acres. But volume alone doesn't tell the whole story. The material being deposited had to meet precise engineering specifications. Loose, wet sand pumped from the ocean floor is essentially unstable. Slurry, it compresses unpredictably, shifts under load, and drains unevenly. Drop industrial equipment on top of it prematurely and you don't get a refinery. You get a very expensive sinking disaster. So every layer of deposited material had to be monitored, tested, and verified before the next layer went down. Engineers tracked settlement rates, how quickly the new land was compressing under its own weight, because premature loading on undersettled fill is one of the fastest ways to compromise a foundation irreparably. Then came the most painstaking part of all: waiting. Land reclamation isn't just a construction process, it's a geological one. New land needs time to consolidate, to expel trapped water, to reach a stable bearing capacity. At Zhoushan, engineers used a technique called surcharge preloading. essentially piling extra weight on top of the reclaimed land intentionally, forcing it to compress faster than it would naturally. This accelerated the consolidation timeline, but it still took years, and the entire time, the sea didn't cooperate. Tidal forces pushed against the containment berms, storm surges tested the perimeter walls. The ocean was constantly working against the construction, eroding edges, destabilizing fill zones, challenging every calculation the engineers had made. But every cubic yard of material placed, every layer tested, every settlement reading logged was a step towards something that had never existed before: stable, load-bearing ground in the middle of an active tidal zone, ready to hold one of the heaviest industrial complexes ever built. The land was taking shape, but land alone wasn't enough. What came next would determine whether any of it could actually hold what China was planning to put on top of it. Building ground that won't sink. You now have an island, but an island made of compacted fill and dredged sediment isn't the same as natural ground. Natural ground has had thousands of years to consolidate, compress, and reach equilibrium. Reclaimed land has had years, sometimes less, and the Zhejiang complex wasn't going to sit light on this surface. It was going to crush it with the weight of thousands of industrial units, storage tanks holding millions of barrels of liquid, and pipeline networks running in every direction beneath the surface. The ground had to be engineered to perform like bedrock, and that meant going deep. The primary technique used was vertical drain installation combined with surcharge loading, a method that forces water out of saturated soil by creating drainage pathways and then pressing down hard from above. Thousands of vertical drains were driven into the reclaimed fill across the entire footprint, essentially giving trapped water a route to escape. Without these drains, the consolidation process would have taken decades. But even accelerated consolidation wasn't enough for the most critical zones, the areas directly beneath refinery towers, distillation columns, and storage tanks. These locations required ground improvement at a completely different level. Engineers used deep soil mixing and cement grouting to chemically bind loose particles together, creating reinforced soil columns that could transfer enormous loads down to more stable layers below. Then came the monitoring systems. Across the entire reclaimed platform, sensors were embedded to track ground movement, settlement rates, and pore water pressure in real time. Because even after construction begins, reclaimed land continues to settle slowly, incrementally, but continuously. If one zone settles faster than another, the differential movement creates stress concentrations that can crack foundations, buckle pipelines, and misalign equipment worth hundreds of millions of dollars. This was the tension that engineers lived with every single day, building on a surface that was still technically in motion. And here's what makes it remarkable. They didn't just manage that risk. They engineered around it so precisely that the complex could be constructed, commissioned, and brought to full operational capacity without a single catastrophic ground failure across thousands of acres of artificial land. The ground held, but holding the ground was only half the battle. Because sitting on top of that ground would be structures so heavy, so tall, and so mechanically complex that they needed foundations of an entirely different magnitude. A foundation for giants. When you think about foundations, you probably think about concrete and rebar, the basic bones of any building. But the foundation systems required for an industrial complex of this scale aren't comparable to anything in conventional construction. You're not anchoring office towers or apartment blocks. You're anchoring distillation columns that stand over 200 feet tall, pressure vessels weighing thousands of tons, and storage tanks with diameters wider than a football field. On natural ground, you drill down to bedrock and anchor there. On reclaimed land over open water, bedrock can be hundreds of feet below the surface, below layers of fill, sediment, and soft marine clay that offers almost no structural resistance. That gap has to be bridged entirely by engineering. The solution at Zhoushan was driven pile foundations, steel and concrete piles, hammered or drilled down through the reclaimed fill and soft sediment layers until they reached competent bearing strata deep below. For the heaviest equipment, pile depths exceeded 150 feet. Across the entire complex, the number of individual piles driven into the ground runs into the tens of thousands. But the piles alone weren't the end of it. At the surface, those piles were connected by massive pile caps, reinforced concrete platforms that distribute load across multiple piles simultaneously. This load-sharing system meant that even if one pile encountered slightly weaker soil, the surrounding piles absorbed the difference. No single-point failure, no weak link. Then came the coastal reinforcement challenge. The perimeter of the island, the edge where artificial land meets open sea, is one of the most vulnerable zones in any reclamation project. Wave action, tidal scour, and storm surge all attack this boundary continuously. If the perimeter fails, the interior fails with it. At Zhoushan, the coastal boundary was reinforced with rock armor, sheet pile walls, and concrete revetment systems designed to absorb and deflect wave energy rather than resist it directly. The result was an artificial landmass that didn't just sit on the ocean, it was anchored to it, armored against it, and engineered to outlast it. And now, with stable ground beneath and foundations driven deep, the next challenge was equally monumental, connecting this island to the global oil supply. Because an oil refinery with no way to receive crude oil is just an extraordinarily expensive piece of real estate, bringing in the world's biggest ships. An oil refinery runs on crude oil, and crude oil, at the scale the Zhejiang complex demands, doesn't arrive by pipeline from a nearby field. It arrives by sea on tankers so large they belong to a category of vessel that most ports in the world simply cannot accommodate. The vessels that supply a complex like Zhejiang are called very large crude carriers and ultra-large crude carriers, VLCCs and ULCCs. A fully loaded VLCC carries roughly 2 million barrels of crude oil. It displaces over 200,000 tons of water when full. It needs a minimum water depth of around 70 feet just to float safely near a berth. And it needs specialized mooring infrastructure, loading arms, and offloading systems capable of transferring that oil quickly enough to keep the refinery's supply chain moving without interruption. This is exactly why Zhoushan was chosen. The deep natural water around the archipelago gave engineers a starting point that most coastal locations simply can't offer. But deep water near a coastline doesn't automatically mean a functioning deep-water terminal. That still had to be built. The port infrastructure at the Zhejiang complex includes dedicated berths engineered specifically for VLCC-class vessels. The approach channels were dredged and maintained to ensure navigable depth under all tidal conditions. Mooring systems were designed to hold vessels of over 1,000 feet in length, stable against tidal currents and wind loading, while transfer operations are underway. But here's the tension that port engineers had to solve. Offloading 2 million barrels of crude oil from a single vessel isn't just a logistics problem, it's a pressure management problem. The offloading rate has to be calibrated precisely against the refinery's intake capacity and storage tank availability. Move too fast, and you overwhelm the receiving infrastructure. Move too slow, and you back up the entire tanker queue, costing millions in vessel demurrage fees per day. The solution was an integrated port and refinery control system that monitors flow rates, tank levels, and vessel status in real time, coordinating the entire offloading operation as a single continuous process rather than a series of disconnected steps. And once that crude oil leaves the tanker, it doesn't travel far before it enters a system more complex than anything. The port itself contains a refining and petrochemical network, so tightly engineered that nothing that enters it goes to waste. The refinery itself. You've seen the island built. You've seen the foundations driven deep and the tankers guided in. Now the crude oil is flowing onshore, and what happens next is where this entire project justifies every dollar spent and every ton of material moved. Crude oil, in its raw form, is almost useless. It's a thick, dark mixture of hundreds of different hydrocarbon compounds, each with different boiling points, different molecular weights, and different industrial applications. Before it becomes jet fuel, diesel, gasoline, or the feedstock for plastics and chemicals, it has to be separated, cracked, and refined with extraordinary precision. The first stop is the crude distillation unit, the heart of any refinery. Here, raw crude is heated to extreme temperatures and fed into a distillation column where different hydrocarbon fractions separate based on their boiling points. Lighter fractions rise to the top. Heavier ones sink to the bottom. Each fraction exits at a different level and moves into its own dedicated processing stream. But this was just the beginning of the transformation. The heavier fractions, the ones that don't separate, easily go through catalytic cracking, a process that uses heat, pressure, and chemical catalysts to break large hydrocarbon molecules into smaller, more valuable ones. This is how a barrel of crude that might otherwise yield mostly heavy fuel oil gets converted into high-value gasoline and diesel instead. At the Zhejiang complex, the catalytic cracking capacity operates at a scale that pushes the boundaries of what single-site refining has ever achieved. Then comes hydroprocessing, where impurities like sulfur, nitrogen, and metals are stripped out of the refined streams, producing cleaner fuels that meet modern environmental and commercial standards. Every stream, every fraction, every output has a destination and a value. Nothing is wasted. The result is a refinery that doesn't just process crude oil, it extracts maximum value from every single molecule that enters the system. At 800,000 barrels per day of processing capacity, even marginal efficiency gains translate into hundreds of millions of dollars in additional output annually. And here's what most people don't realize. The refining operation is only one layer of what this complex does. Sitting directly alongside it is a petrochemical system that takes the refinery's outputs and transforms them into something far more valuable than fuel. The petrochemical layer. Fuel is a commodity. Chemicals are a different business entirely. And the Zhejiang complex was never designed to stop at refining. It was designed to go several steps further, turning refined hydrocarbon streams into the raw materials that modern industrial economies run on. The petrochemical units at Zhejiang sit integrated directly with the refinery, which is a critical engineering distinction. In a standalone petrochemical plant, feedstocks have to be purchased, transported, and delivered from an external source. Here, the feedstock flows directly from the refinery next door, through internal pipelines. No transport cost, no supply chain delay, no margin lost to intermediaries. The flagship product of this petrochemical layer is paraxylene, commonly known as PX, a chemical compound that serves as the primary feedstock for polyester fiber and PET plastic. Everything from clothing to plastic bottles to packaging film depends on a steady supply of PX. China is the world's largest consumer of polyester, and domestic PX production has historically lagged far behind domestic demand, forcing expensive imports. The Zhejiang complex was built, in part, to close that gap permanently. But the petrochemical ambition didn't stop at PX. The complex also produces ethylene, the single most important building block in the global chemical industry. Ethylene feeds into the production of polyethylene plastics, antifreeze, solvents, and dozens of other downstream materials. Producing it on-site, integrated with a refinery of this scale, gives Zhejiang a cost structure that standalone petrochemical facilities simply cannot match. Then came the most strategically significant realization of all. By combining refining and petrochemicals on a single integrated platform, the Zhejiang complex can dynamically shift output between fuel production and chemical production, depending on which market offers better margins at any given moment. When fuel prices are high, dial up refining output. When chemical demand spikes, redirect feedstocks into the petrochemical units. This flexibility is worth billions. No other facility in the world operates this integration at this scale in a single location. And feeding all of it, the refinery, the petrochemical units, the storage systems. The port is an internal infrastructure network so complex that it functions less like a set of pipes and more like the circulatory system of an entire industrial city. Pipelines, tanks, and flow. You could build the most advanced refinery on the planet, but without the infrastructure to move product through it, around it, and out of it, you have nothing. The Zhejiang complex understood this from day one, and the internal logistics network it operates is as impressive as any single piece of processing equipment on the island. Start with the storage tanks. Before crude oil enters the refinery, it needs to be held in buffer storage enough to keep the refinery running, even if tanker deliveries are delayed by weather, port congestion, or supply chain disruption. The tank farms at Zhejiang hold tens of millions of barrels of crude and refined products simultaneously. Individual tanks in complexes of this scale can reach over 300 feet in diameter and hold over 1 million barrels each. Lined up side by side across the reclaimed land, They represent one of the largest concentrations of liquid hydrocarbon storage anywhere on Earth. But storage is static. What makes it functional is movement, and that means pipelines. The internal pipeline network at the Zhejiang complex runs for hundreds of miles across the island footprint, connecting every tank, every processing unit, every loading berth, and every export terminal into a single integrated flow system. Different pipelines carry different products at different pressures and temperatures. Crude oil lines run at high volume and low pressure. Refined product lines carry lighter, more volatile materials that require pressure regulation and vapor recovery systems. Steam lines, cooling water lines, chemical injection lines, and instrument air lines layer underneath and alongside all of it. Then came the control challenge, managing this entire network in real time. A leak, a pressure spike, or a flow imbalance in the wrong location at the wrong time doesn't just cause a production disruption. In a facility handling this volume of hydrocarbons, it creates a safety emergency. The entire pipeline and tank farm system is monitored through a centralized distributed control system. Thousands of sensors feeding real-time data to operators who can isolate, reroute, or shut down any section of the network within seconds. The island breathes crude oil in through its ports, processes it through its refinery and chemical units, stores the output in its tank farms, and exhales finished product through its export terminals. Every component depends on every other component operating without failure. And all of this engineering, all of this infrastructure, all of this complexity, it wasn't built just to make fuel. It was built to execute a strategy that reaches far beyond the island itself. China's energy calculation. Nothing about the Zhejiang complex was accidental. Every design decision, every engineering choice, every $1 billion invested traces back to a strategic calculation that China had been running for decades, and the answer it kept arriving at was the same. Energy dependence is a national vulnerability, and the only way to eliminate that vulnerability is to build your way out of it. For years, China imported not just crude oil, but refined products, fuels, and chemicals processed in refineries overseas, in countries with their own economic and political interests. Every barrel of refined product imported was a barrel of value-added manufacturing that happened somewhere else, employed someone else, and strengthened someone else's industrial economy. China decided that era was over. The Zhejiang complex was designed to absorb raw crude from anywhere in the world, Middle Eastern, Russian, African, South American, and convert it domestically into the fuels and chemicals that China's economy demands. By controlling the refining step, China captures the value-added margin that previously flowed to foreign processors. By integrating petrochemicals, it extends that capture further up the value chain. But the strategy goes deeper than economics. A country that can refine its own crude at domestic scale is a country that can sustain its industrial economy even when global supply chains are stressed, when shipping lanes are disrupted, when sanctions are threatened, when geopolitical tensions spike. A nation with this kind of domestic processing capacity has options that energy-dependent nations simply don't have. And Zhejiang isn't alone. It's the flagship of a broader Chinese investment in domestic refining and petrochemical capacity that has systematically reduced China's exposure to external processing bottlenecks. But Zhejiang is the crown jewel, the single largest, most integrated, most strategically positioned facility in that entire network. The world's other major refining powers noticed. Because when a facility of this scale comes online, it doesn't just serve the country that built it. It reshapes the global markets that everyone else depends on too. An island that rewrote energy. Here's where everything you've seen comes together. The reclaimed land, the driven piles, the deep water berths, the cracking units, the chemical plants, the tank farms, the pipelines, and reveals what it actually is at the highest level. The Zhejiang Petrochemical Complex changed the direction of global crude oil flows. When a facility processes 800,000 barrels per day, the tankers supplying it don't come from one region, they come from everywhere. Routes that previously terminated at refineries in Europe, the Middle East, or Southeast Asia now route through Zhoushan, Crude grades that previously had limited buyers now have a guaranteed destination. The complex single-handedly expanded the market for certain crude varieties simply by having the technical capability to process them. On the refined product side, the impact was equally seismic. China's domestic refining surplus, partially driven by Zhejiang, turned the country from a net importer of certain refined products into a net exporter, flooding regional markets in Asia with competitively priced diesel, gasoline, and chemical feedstocks. Refineries in neighboring countries felt the pressure immediately. Margins compressed. Some older, less efficient facilities became economically unviable almost overnight,